Fired through a vacuum, a charged particle travels in a straight line. Introduce a magnetic field, and its path violently hooks into a curve. This behavior is governed by the Lorentz magnetic force rule. The force exerted on that particle is the cross product of its velocity and the magnetic field it travels through. Because it is a cross product, a single variable dictates the geometry of the particle's future path, the angle between the particle's initial trajectory and the field lines. We can systematically map the boundaries of this motion. Depending on that entry angle, the resulting path will always fall into one of three geometric states: a straight line, a circle, or a helix. While the tracks of subatomic particles might look chaotic, they are actually perfectly predictable geometric constructs, provided we know that entry angle. This outlines case 1, motion perfectly parallel at 0 degrees or anti-parallel at 180 degrees to the field. Magnetic force is charge times velocity times field strength multiplied by sine of the angle. Since sine of 0 or 180 is 0, the force is exactly 0. Linear momentum is conserved perfectly. The path remains a straight line. Now we test the opposite extreme, case 2, where the particle enters perfectly perpendicular to the field lines, exactly 90 degrees. We represent this inward-pointing field using a grid of x's. At 90 degrees, the magnetic force acts strictly perpendicular to velocity, pulling towards center point O, exactly like centripetal force. Equating the centripetal force equation, mv squared over r, to our magnetic force, qvb, we can isolate the orbital radius, r. Notice the term q over m. We define this ratio as the specific charge, alpha, a fixed material property. These two extreme angles set our baseline. They determine whether a particle completely ignores a magnetic field and flies straight, or becomes entirely trapped by it in a closed loop. To engineer real systems, we must express this radius dynamically. Using raw velocity isn't enough. We need to tie it to measurable energy states. Looking at these equations, in the radius formula, mass times velocity can be swapped for p, linear momentum. Momentum is then converted into kinetic energy, k, placing the term under a square root. Finally, we convert kinetic energy into voltage, v, the active dial an engineer turns to control the particle's radius. This chart tracks time. The period, t, to complete one orbit is the circumference, 2 pi r, divided by velocity. Substituting our previous radius formula into this equation reveals a mathematical paradox. The velocity term cancels out completely. This means the angular velocity, period, and frequency are strictly independent of speed. A faster particle will carve a wider circle, but it will complete the lap in the exact same time as a slow one. We move now to case 3. This is the general state where the entry angle is oblique, falling somewhere between strict 0 and 90-degree conditions. Here, we decompose the oblique entry velocity into two components. The perpendicular component, v sine theta, dictates the circular radius of the path. The parallel component, v cosine theta, experiences 0 magnetic force, moving at a constant speed, stretching that circle into a helix. We define pitch, key, as the linear distance traveled parallel to the field in one orbital period. Multiplying parallel velocity by period t gives the pitch formula. Any complex three-dimensional helical path is simply the simultaneous superposition of a 2D circle and a 1D straight line. In engineering reality, magnetic fields are rarely infinite. They exist in bounded zones of finite width, which we label d. This diagram illustrates our first scenario. Field width d is larger than the particle's orbital radius, r. Having room to turn, the particle makes a perfect U-turn and exits the way it came, spending exactly half its time period inside the field. In scenario 2, we analyze what happens if the particle enters the field at an offset angle, alpha. The equation shows transit time is strictly scaled by this angle, creating an arc that subtends exactly to alpha. This diagram outlines scenario 3, screen deflection, where field width d is smaller than radius r. The particle punches through the narrow boundary before turning. By analyzing the right triangle formed by entry and exit points, we calculate the deflection angle, theta, as the ratio of field width over radius. This gives the exact screen coordinates, with y relying on subtracting the horizontal cosine projection from the total radius. By intentionally bounding the magnetic field, we can transform theoretical circular orbits into precise, mathematically guaranteed aiming mechanisms. The motion of any charged particle in a uniform field is entirely deterministic. It is driven by an interconnected web of geometry and energy. Initial velocity components build the radius, while field boundaries leverage that radius to calculate exact strike coordinates. These whiteboard derivations translated directly into the experimental physics of the 20th century. The specific charge isolation we derived earlier is the literal operational foundation of mass spectrometry, allowing engineers to identify elements by their mass-to-charge ratios. The math of bounded field deflection dictates the internal engineering of particle separators and sensors, reflected in this semicircular housing built for those U-turn trajectories. And calculating voltage-dependent radius paths gave birth to the early cathode ray tubes and particle accelerators. Mastering Lorentz kinematics provides the mathematical scaffolding required to steer and manipulate the fundamental building blocks of the universe.